Swayam Prabha. Digital India. Educated India.
Welcome to lecture 26 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is Distributed Lag Models. The impact of that investment on its profit may not be immediate. It may take some period to show the impact of investment on the profit. So, suppose we denote profit by y t, then y t is not just affected by x t, but it is affected by some lagged values of x t. So, any decision made may not have immediate impact, whether you consider any economic decision or any decision in banking sectors or any financial sector, industrial sector, etc. So, it may take certain time, certain lag. The objective of distributed lag models is to model such kind of phenomena. Then different lags may have different impacts. Say for example, some bank decides to make changes in its interest rates. Then it may have certain impact after 1 year, it may have some impact after 2 years, etc. But for different lags it may have different impacts. So, while modeling such kind of phenomena, we must incorporate the variables of different lags. Not only that, we should assign different weights to different lagged variables. In this lecture, we will consider distributed lag models when the number of lags considered is finite as well as infinite. So, we will consider both the finite distributed lag models as well as infinite distributed lag models. We will also discuss the estimation procedures for these models, or how to select the number of lags in finite distributed lag models. So, different model selection criterion can be used for selecting the number of lags. We will discuss those model selection criterion in this lecture. So, we consider distributed lag models. One or more lagged values of x's or y's as determinants of the current value y t are included on the right hand side. So, your exogenous variables are not just the current values of x's or y's. In fact, we do not include the current values of y's, we just include the current values of x's. But in distributed lag models, we also include some lagged values of x's, and in some models we also include some lagged values of y's. Then why lagged effects appear in an empirical model? So, we consider some examples where we have lagged effects in the model. So, in economic modeling, one may observe lag between the policy changes and their impacts on economic variables, so such as output or investment. So, it may not have immediate effect. You may observe some lag between the policy change and its impact. So, the analysis of lag length, say after how much period it is going to affect of impact on economic variables is utmost important. So, this is quite important to investigate the analysis of lag length. Then lag terms appear when either the dependent variable or some independent variable is based on expectations or forecasts. So, sometimes your current value of y t may depend upon some forecasted value of x t for the period t. So, it is not the exact value of x t, but it is forecasted value of x t. So, in that case also we use distributed lag models. Say for example, forecasts of prices of income play a crucial role in demand function. So, in demand function you include say either prices or income, but for that particular period you may not have exact observations on prices or income. So, instead of using the exact income or exact prices, you use the predicted values of income or predicted value of prices. So, then again you require distributed lag models, you get some kind of lag in your model, lag effect. Then investment decisions on a stock not only depend upon its current price, but also on its past prices history. So, suppose you want to invest in some particular stock, then you of course, you consider its current price, but you also consider its past history, the past price history. So, your decision is not just based on the current price of the stock, but how this stock has behaved in the past. This is also important for making investment decision. Then the effect of public investment such as road and highways construction on growth in the gross national product GNP will show up with a lag. So, suppose the government has decided to make certain amount of investment in the infrastructure sector, say in road and highways construction or in electricity, etc. Then such kind of decisions, such kind of investments have impact on the GNP, but such kind of investment do not have immediate impact on GNP. These investments start showing effect after certain period. So, while modeling GNP using investment on infrastructure as one of the explanatory variable, you not only consider the current investment on infrastructure, but lagged values of investment on infrastructure also in your model. Say the current value of GNP may depend upon one period lagged value of investment on infrastructure with certain weight. Then 2 years lag period of investment on infrastructure with some other weight, etc. Now, we define the lag operator. The lag operator L is defined as L x t is equal to x t minus 1. Then we define L r x t equal to x t minus r. So, L r gives you the r period lagged values of x t. Then we define difference operator, delta x t is equal to x t minus 1. So, obviously, you can write delta equivalent to 1 minus L. Delta x t is equal to 1 minus L x t. Then delta square x t is equal to, we take delta x t first and then we take the difference of delta x t. So, x t minus 1 minus x t minus 1 minus x t minus 2. So, this is equal to x t minus twice x t minus 1 plus x t minus 2, and you may denote it by 1 minus L whole square x t, because 1 minus L whole square is equal to 1 minus twice L plus L square and if we take x t here, then you get x t minus twice x t minus 1 plus x t minus 2. Now, first we consider the finite distributed lag models. So, suppose you have variables y t, x t and u t, t equal to 1 to n, and all these variables are stationary and ergodic processes. So, by stationarity we mean the probability mechanism which has generated the time series do not change over time, and the way process changes is predictable. So, the whole purpose of defining stationarity is that the way process changes is predictable. You can predict the process, and then we define the stationarity as a process y t is said to be stationary if the joint distribution of y t 1, y t 2, so on y t n is the same as the joint distribution of y t 1 plus k, y t 2 plus k, so on y t n plus k for all n t 1, t 2, t n and k. So, this is the definition of stationarity. So, we assume that y t's, x t's and u t's are stationary. Then we define ergodic process. So, stationarity ensures statistical equilibrium. You have some kind of equilibrium. The distribution does not change if you replace t 1 by t 1 plus k, t 2 by t 2 plus k, so on t n by t n plus k. So, if you shift the entire time series by k period, then the distribution does not change. So, stationarity ensures statistical equilibrium, but not its uniqueness. Ergodicity along with stationarity ensures that such an equilibrium is unique. So, you also require this condition. The process is not only stationary, but you also want to ensure that it approaches to a unique equilibrium state, and this is the purpose of defining ergodicity. So, ergodicity ensures that a single long time series becomes representative of the whole data generating process, just like a large IID sample becomes representative of the whole population or distribution. Now, remember that when you have time series observations, then at each time point you have just a single observation, and then for different time points the process changes its nature. So, you want to ensure that a single long time series is the representative of whole data generating process. Say in usual IIT sample, your sample is representative of the entire population or distribution. Same thing you want here also. So, a process y t is said to be ergodic with respect to a bounded function, say f, if 1 upon n summation f y t converges almost everywhere as n tends to infinity. Now, by stationarity, we ensure that expectation of f y t say is equal to mu. The distribution does not change. So, if you take expectation, expectation also does not change. So, expectation of f y t is equal to mu for all t, but the stationarity does not ensure that this expectation is unique, or 1 upon n summation f y t converges to a unique value. Now, by ergodicity, we ensure that 1 upon n summation f y t converges almost everywhere as n tends to infinity, and expectation of f y t is mu. So, it ensures that 1 upon n summation f y t converges to mu. Now, first we consider the unrestricted finite distributed lag model. So, we define y t equal to beta naught plus summation I equal to 1 to p beta I x t minus I plus u t, and by x t, suppose we denote the vector 1 x t minus 1 x t minus 2, so on x t minus p. Then this x t satisfies the condition 1 upon n summation t x t transpose converges in probability to Q a finite positive definite matrix as n tends to infinity. So, we require this condition and then probability limit as n tending to infinity 1 upon n summation over t x t u t is equal to 0. So, in limit x t is uncorrelated with u t. So, these are the two assumptions which we make. Now, first we assume that the lag length p is known and it is fixed. Then you can write the model 1 as y equal to x beta plus u. So, it is just a simple linear regression model, where y is equal to y 1 y 2 y n transpose, beta is beta naught beta 1 so on beta p transpose, and u is equal to u 1 u 2 u n transpose. So, again y is n cross 1 vector, this beta is p plus 1 cross 1 vector, and u is n cross 1 vector. And then we define capital X as it has columns x 1, x 2, x n, x naught, x 1, so on x n minus 1 and so on, x minus p plus 1, x minus p plus 2, so on x n minus p. Actually, it is n cross p plus 1 matrix. And we assume that expectation of u is equal to 0, expectation of u transpose is equal to sigma square u I n. Then you can easily find the OLS estimator of beta. You simply apply the OLS procedure. So, the OLS estimator is B equal to x transpose x inverse x transpose y. And then obviously, B is consistent and asymptotically normal. Under these two conditions, B is consistent as well as asymptotically normal. Now, a problem with the finite distributed lag models is that you usually do not have the idea of lag length. So, you have to estimate the lag length. For that purpose, we use different information criterion. Say, suppose you want to estimate lag length using AIC, the Akaike information criterion. Then for the given value of p, AIC p is equal to log sigma head square p. This is the estimator of sigma square u based on a distributed lag model of lag length p plus twice p upon n. So, sigma head square p is the MLE of sigma square u based on lag length p, and p head is the argument minimum AIC p, p equal to 0 1 so on, say p n. P n is the maximum lag length which we are going to consider. So, p head is that value of p for which AIC is minimum. We find that value of p for which this is minimum, and that value of p gives you an estimate of the lag length. Then apart from AIC, we may consider some other criterion also. Say you may consider BIC, which is defined here, Bayesian information criterion, or you may use the prediction criterion p is equal to sigma head square p n plus p plus 1 upon n minus p plus 1. You may also use Mallow's CP criterion, which is defined as CPP equal to sigma head square p plus twice p sigma head square upon n, where sigma head square is equal to n sigma head square p n upon n minus p n minus 1. So, remember the maximum lag length which we have considered is p n, and then this is the estimator of sigma square u based on the maximum lag length. Now, there are some problems with the finite distributed lag models. So, if the values of x t do not change much and move closely to mean, then columns of x are nearly linearly dependent. Remember that you have say x t minus 1 so on, these values involved in your model. And if all these values do not change much and all these values are very close to the mean, say you take the mean as x bar. So, all these values are not very different from the mean. Then the columns of X matrix are nearly linearly dependent, and then you face the problem of multicollinearity, because X transpose X is nearly singular. Of course, you can use some other method, some estimator other than the least square estimator, like you may use Ridge regression estimator for estimating beta. Then the practical approach is to express lag coefficients as functions of few parameters. So far in finite distributed lag models, you have considered different coefficients beta j's. One possibility is that we express these coefficients beta j's as functions of few parameters. So, first we consider arithmetically declining lag. So, in arithmetically declining lag, we take beta I equal to p plus 1 minus I into alpha. So, the lag coefficients decline arithmetically. Say for example, for I equal to 1, beta 1 is equal to p alpha. For I equal to 2, beta 2 is equal to p plus 1 minus 2, that is p minus 1 alpha. I equal to 3, beta 3 is equal to p minus 2 into alpha. So, the lag coefficients are declining arithmetically, and these lag coefficients depend upon alpha. So, although the original model has the coefficients beta naught, beta 1, so on beta p, but if you define beta I in this manner, then ultimately you have just one coefficient alpha. Then another option is inverted V lags. So, in arithmetically declining lags, all the coefficients are declining arithmetically, but it may happen that say 2 period lag value has maximum weight, say beta 2 has maximum weight. In arithmetically declining lag, such kind of possibility is not there. Say any change in economic policy, say any change in interest rate or any investment in infrastructure may have maximum impact after 2 years. So, beta 2 is maximum, and before that you have values of betas lower than beta 2, and after that again the values are declining. So, you have inverted V lag, beta 2 is maximum, or it may be beta 4 which is maximum, and then beta 2 or beta 3 or beta 1 are less than beta 4. So, you get some kind of inverted V lag. So, to model such kind of phenomena, we take beta I equal to I plus 1 alpha for I greater than or equal to 0, less than or equal to s. So, up to I equal to s, these weights are linearly increasing, and then for I lying between s plus 1 to p, beta I is equal to p minus I plus 1 into alpha. So, after this point s, the weights are declining linearly. So, you get a inverted V lag shape. Here the maximum value which you get is at I equal to s. So, these two lag schemes are inflexible and less frequently used. So, this is the problem with these two lag schemes. These lag schemes are not very flexible. So, in first lag scheme you can model the lag where you have weights just linearly increasing. In the second lag scheme, if you have this kind of inverted V shape for the lag coefficients, then you can use this kind of lag weights. In Almond distributed lag model, we have the model y t equal to beta naught plus summation I equal to 1 to p beta I x t minus I plus u t, and then lag weights are represented as a polynomial of degree q, and obviously q is less than p. So, we represent beta I as alpha naught plus alpha 1 I plus alpha 2 I square so on plus alpha q I to the power q, I equal to 0 1 so on p. Now, this kind of representation of coefficients is quite flexible. Say you may cover the linearly increasing lag weights. If you consider just this part, then lag weights are linearly increasing, or suppose lag weights have this kind of shapes, which is quite close to the inverted V shape, then you can use a second degree parabola to represent this kind of shape, etc. So, this kind of representation is quite flexible. Now, if we combine 1 and 6, then we obtain y t equal to, you write beta naught, means for I equal to 0, beta naught is equal to just alpha naught. For I equal to 1, beta 1 is equal to alpha naught plus alpha 1 plus alpha 2 so on plus alpha q, because you are taking I equal to 1. So, in general you can write y t equal to, you have alpha naught here plus beta 1 is equal to alpha naught plus alpha 1 plus so on plus alpha q into x t minus 1 plus alpha naught into 2 plus 2 to the power 0, which is 1 plus alpha 1 2 to the power 1 plus alpha 2 2 square plus so on plus alpha q 2 to the power q, and then you have x t minus 2 here plus so on. J t is equal to summation I equal to 0 to p I to the power j x t minus I for all j equal to 0 1 so on q, and then you can write it as beta equal to h alpha. You have the relations beta I equal to alpha naught plus alpha 1 I plus so on plus alpha q I to the power q, and then we write it in the vector and matrix notations. So, you get then j t is equal to summation I equal to 0 to p I to the power j x t minus I for all j equal to 0 1 so on q. Further, using vector and matrix notations, we can write the relation between beta and alpha as beta equal to h alpha, where alpha denotes the vector with elements alpha naught, alpha 1 so on alpha q, and H is the matrix with first column consists of all elements equal to 1, the second column is 0 1 2 so on p, third column is 0 1 square which is again equal to 1, then 2 square so on p square and so on. The last column is 0 1 2 to the power q so on p to the power q. You can easily verify that h alpha is equal to, the first element of h alpha is 1 into alpha naught plus 1 plus 0 into alpha 1 so on plus 0 into alpha q. So, it is alpha naught. Then the second element is 1 into alpha naught plus 1 into alpha 1 so on plus 1 into alpha q. So, alpha naught plus alpha 1 plus so on plus alpha q. So, again for I equal to 1, what you get? Beta 1 equal to alpha naught plus alpha 1 plus alpha 2 so on plus alpha q, this second element, and so on. The last element is 1 into alpha naught plus p into alpha 1 plus p to the power q into alpha q. So, for I equal to p, what you get? Beta p equal to alpha naught plus alpha 1 p plus alpha 2 p square so on plus alpha q p to the power q. So, you get this last element. So, between the coefficients beta and alpha, you have this relation beta equal to h alpha. Then you can write the model as y equal to x h alpha plus u. We replace beta by h alpha, and then we write x h equal to z. So, you get the model y equal to z alpha plus u. Then the least square estimator of alpha is alpha hat equal to z transpose z inverse z transpose y. And obviously, under the assumption of normality of disturbances, this follows a normal distribution having mean vector alpha and variance covariance matrix sigma square u z transpose z inverse. Now, using this OLS estimator of alpha, you can easily estimate beta also, because the relation between beta is and alpha is beta equal to h alpha. So, you estimate beta as beta hat equal to h alpha hat, and then alpha hat is equal to, you get h into z transpose z inverse z transpose y. Again z transpose z inverse z transpose y follows normal distribution with mean vector alpha and variance covariance matrix this. So, h alpha hat follows a normal distribution with mean vector h alpha, which is equal to beta, and variance covariance matrix is sigma square u h z transpose z inverse h transpose. So, this is the variance covariance matrix of beta hat. Again, a problem with finite distributed lag models is that these finite distributed lag models impose strong restrictions on the functional form of the model. So, you have imposed this kind of restriction, say beta equal to h alpha on the coefficients. So, you have some strong restrictions on the functional form of the model. Now, we consider infinite distributed lag models. So, suppose y t is the dependent variable and x t is explanatory variable, then your general model is y t equal to beta naught x t plus beta 1 x t minus 1 so on. So, you get the terms up to lag infinity in your model plus u t, or you can write it as y t equal to beta L x t plus u t, where beta L is defined as the lag operator beta naught plus beta 1 L plus beta 2 L square and so on. So, obviously, beta L x t is equal to beta naught x t plus beta 1 x t minus 1 so on. Now, it is not possible for you to estimate the coefficients of this infinite distributed lag model directly. Actually, the model has infinite number of parameters beta naught, beta 1 so on. So, you have infinite number of parameters. So, on the basis of a finite number of observations, say you have n number of observations and is finite, you cannot estimate infinite number of parameters. It is not possible for you, unless you impose some conditions on these coefficients. or some conditions on the functional form of these coefficients. You assume some kind of functional form for these coefficients betas. So, we consider some special cases, say geometric lag model. In geometric lag model, we assume that beta I is equal to alpha into 1 minus lambda into lambda to the power I, for I equal to 0, 1, so on. So, these coefficients are declining geometrically. For I equal to 0, you get beta naught equal to alpha into 1 minus lambda. For I equal to 1, you have the coefficient beta 1 equal to alpha 1 minus lambda into lambda and so on. So, although in the original model you have infinite number of beta i's, but if we assume this kind of functional form for beta i's, then in the actual model you have just two parameters, alpha and lambda, and these coefficients beta i's are now declining geometrically. The common ratio is lambda, and obviously we assume that lambda I lies between 0 and 1. So, these lag weights W i's equal to 1 minus lambda, lambda to the power I are lie between 0 and 1, W I lies between 0 and 1. So, these weights are declining geometrically. Then you can write the model as y t equal to beta naught is equal to alpha into 1 minus lambda plus alpha into summation I equal to 1 to infinity 1 minus lambda into lambda to the power I x t minus I plus u t. So, we have substituted the value of beta I here, or we write it as B L x t plus u t, where B L is equal to alpha into 1 minus lambda plus for I equal to 1 you get alpha into 1 minus lambda into lambda, and then you have lag operator here, actually x t minus I is equal to L I x t plus again you have alpha into 1 minus lambda into lambda square L square and so on. And then we write it as, actually this is equal to alpha into 1 minus lambda upon, here actually you have a geometric series. So, you can write it as 1 upon 1 minus lambda L. You have infinite geometric series here. So, B L is equal to alpha into 1 minus lambda upon 1 minus lambda L. Now, mean lag, mean of all these weights is, so you have 0 into W naught plus 1 into W 1 plus 2 into W 2 and so on. Then W j is equal to 1 minus lambda into lambda to the power j. So, you take 1 minus lambda common here and you get 1 into lambda plus 2 into lambda square plus so on. And suppose you want to find the sum of this series, 1 into lambda plus 2 into lambda square plus 1. So, you have this infinite series, you multiply s by lambda. So, you get 1 into lambda square plus 2 into lambda cube plus 1, and then you take the difference. So, you get s into 1 minus lambda equal to, the first term is lambda, again you get lambda square plus lambda cube plus so on. So, you get lambda upon 1 minus lambda. So, s is equal to lambda upon 1 minus lambda square, and then you have 1 minus lambda here also. So, finally, you obtain lambda upon 1 minus lambda. So, this is the mean lag weight. Then median lag is the value p star such that summation I equal to 0 to p star W I is equal to 1 upon 2. Now, you can easily obtain the value of this summation, summation I equal to 0 to p star, this is, and then W I is equal to 1 minus lambda into lambda to the power I. So, basically you get a finite geometric series with the first term 1 minus lambda and common ratio lambda, and then you can easily add that finite geometric series, and then you obtain 1 minus lambda into 1 minus lambda to the power p star plus 1 divided by 1 minus lambda. Again this 1 minus lambda will cancel out, and you write it equal to 1 upon 2. Then using this relation you can easily obtain the value of p star, say lambda to the power p star plus 1 is equal to 1 minus 1 by 2. So, this is equal to say 0.5 we write it. Now, you take log of this. So, p star plus 1 log of lambda is equal to log of 0.5, and from here you obtain p star equal to log 0.5 upon log lambda minus 1. So, this is the median lag. Then the long term multiplier is actually alpha into summation I equal to 0 to infinity 1 minus lambda into lambda to the power I, which is equal to alpha. This is infinite geometric series, and you can easily add it and you get alpha here. Now, in the long run y t tends to y bar, x t tends to its mean x bar, and u t tends to 0. So, the equilibrium value is, say we take in the model y t equal to alpha into 1 minus lambda plus alpha into summation I equal to 1 to infinity 1 minus lambda lambda to the power I x t minus I plus u t. We take y t tending to y bar. So, y bar equal to alpha into 1 minus lambda plus alpha 1 to infinity 1 minus lambda lambda to the power I x bar, and then u t tends to 0. So, you get this solution, and then you can write it as say gamma plus beta x bar. You can easily obtain the value of gamma and beta. Gamma is equal to alpha into 1 minus lambda, and beta is equal to alpha into lambda. Just take the summation of 1 minus lambda into lambda to the power I. So, you get this value of beta. Now, we consider Pascal lag model. In Pascal lag model, you take B L equal to alpha 1 minus lambda to the power m upon 1 minus lambda L to the power m, where lambda lies between 0 and 1, and m is any positive integer. So, if you take m equal to 1, then you get the geometric lag model. So, we have just modified the geometric lag model, and instead of 1 minus lambda you have taken 1 minus lambda to the power m here, and instead of 1 minus lambda L you have taken 1 minus lambda L to the power m here in the expression for B L. Now, in Pascal lag model, an interesting observation is if m is greater than 1, then the lag weights increase first and then taper off. In geometric lag models, the lag weights decrease, but in Pascal lag model, first the lag weights increase and then the weights taper off. So, it is somewhat similar to the inverted V shape model for the finite distributed lag. Then we consider discounted polynomial lag model. So, it is even more flexible than the geometric lag specification, and here in this specification we take B L equal to summation I equal to 0 to infinity lambda to the power I, and then in between you have summation j equal to 0 to r p j I to the power j, and then you have L to the power I. So, obviously, if you take r equal to 0, then you have just one term here which is p naught, and if you take p naught equal to alpha into 1 minus lambda, then you get the geometric lag model. Now, this operator is actually equivalent to B L equal to gamma L upon 1 minus lambda L to the power r plus 1, where this gamma L is of degree r. So, gamma L has degree r and B L has now this form, and as I mentioned earlier, for r equal to 0 we get the geometric distributed lag model. Now, we consider adaptive expectations model. So, suppose y t is the quantity supplied and suppose it depends upon the unobserved expected value, say x t star. Say x t star may be the unobservable expected price for the period t. Then y t is equal to alpha naught plus alpha 1 x t star plus u t. But exact value of x t star is unknown. X t star are revised proportional to error of previous level of expectation. So, x t star minus x t minus 1 star is equal to lambda x t minus x t minus 1 star. So, this is the previous predicted value or expected value, maybe expected price, and this is the expected price for the current period. Now, this is the expected price for the previous period. Now, actual value of the price for the previous period is also known. So, this is the error in predicting the previous period price. So, what you have done here, x t star are revised proportional to error of previous level of expectation. So, you have revised x t star in such a manner that x t star minus x t minus 1 star is proportional to x t minus 1 minus x t minus 1 star, and constant of proportionality is lambda. Lambda lies between 0 and 1. Lambda is called the coefficient of expectation. Then x t minus 1 star is equal to lambda x t minus 1 plus 1 minus lambda x t minus 1 star. You simply take this x t minus 1 star towards the right hand side. So, you get x t star equal to lambda x t minus 1 plus x t minus 1 star minus lambda x t minus 1 star. So, you get 1 minus lambda x t minus 1 star, and then we proceed further and finally, we obtain summation I equal to 0 to infinity lambda 1 minus lambda to the power I x t minus 1 minus I. Again we substitute the value of x t minus 1 star in terms of x t minus 2 star and so on. So, finally, you obtain this value. So, x t star is equal to summation I equal to 0 to infinity lambda 1 minus lambda to the power I x t minus 1 minus I, and then we substitute this value of x t star in your model here. So, you get the model y t equal to alpha naught plus alpha 1 summation I equal to 0 to infinity lambda 1 minus lambda to the power I x t minus 1 minus I plus u t. Now, this is geometrically declining distributed lag model. So, this is actually another interpretation of geometrically declining distributed lag model as the adaptive expectations model. Then we can write this model 13 as y t minus 1 minus lambda y t minus 1 equal to, you simply take y t minus 1 equal to alpha naught plus alpha 1 summation I equal to 0 to infinity lambda into 1 minus lambda to the power I x t minus 1 minus I minus 1 plus u t minus 1, and then you take y t minus 1 minus lambda y t minus 1. So, you get alpha naught minus 1 minus lambda alpha naught, which is equal to lambda into alpha naught. And then here you obtain alpha 1 into lambda. The first term for I equal to 0 is x t minus 1. Now, the second term here is alpha 1 lambda, for I equal to 1 you get 1 minus lambda x t minus 2, and when we subtract 1 minus lambda into y t minus 1, then we have the first term of this is alpha 1 lambda into 1 minus lambda x t minus 2. So, this will cancel out. Similarly, the third term of this summation will cancel out with the second term of expression for y t minus 1 and so on. So, finally, you obtain y t minus 1 minus lambda y t minus 1 equal to alpha naught lambda plus alpha 1 lambda x t minus 1 plus u t. U t star actually, u t star is equal to u t minus 1 minus lambda u t minus 1. And then you can write this relation 14 as say 1 minus 1 minus lambda L y t equal to alpha naught lambda plus alpha 1 lambda L x t plus 1 minus lambda L u t, or you get y t equal to alpha naught plus alpha 1 lambda L upon 1 minus lambda L x t plus u t. So, you get this relation. Similarly, the partial adjustment model is defined as a current value of x t determines the value of y t, and fixed fraction gamma of adjustment is carried out in one period. Say y t star is equal to alpha naught plus alpha 1 x t plus epsilon t, and then y t minus 1 is equal to gamma into y t star minus y t minus 1. So, we adjust the current value of y t like this. Gamma is the coefficient of adjustment. Now, combining equations 17 and 18, we obtain y t equal to gamma alpha naught plus 1 minus gamma y t minus 1 plus gamma alpha 1 x t plus gamma epsilon t. And then here we write y t minus 1 equal to L y t, and then we take 1 minus gamma L y t towards the left hand side. So, on the left hand side we obtain 1 minus gamma L y t, and then it is equal to gamma alpha naught plus gamma alpha 1 x t plus gamma epsilon t. Further, we divide by 1 minus gamma L towards the both sides, so that we obtain y t equal to alpha naught plus gamma alpha 1 upon 1 minus gamma L x t plus gamma upon 1 minus gamma L epsilon t. And here you notice that for any constant c, if we take L c, then L c is equal to c, and therefore we obtain 1 minus gamma L alpha naught equal to 1 minus gamma alpha naught, and then this is equal to gamma alpha naught. Some other distributed lag models which we have not discussed here are the maximum entropy model and optimal adjustment model. Further, for estimating the parameters of distributed lag models, one can use the method of maximum likelihood. So, in this lecture we have discussed different finite and infinite distributed lag models. These models are appropriate for modeling many economic phenomena where the implementation of any particular decision have effect after 1 or 2 years or after the period of some lakhs. So, I am going to stop here. Thank you.
Hi, my name is Gillette Sam and I teach sociology at IIT Kanpur. Today I am going to tell you about an important debate that is occurring around the concept of globalization. Now, within the study of globalization, there are two sets of people. The first set of people argue that globalization is very real. It's something that is happening around us all the time, and in fact, it's something that is gaining strength over time. The second set of people, and the first set of people are called the globalists. The second set of people are not so convinced that globalization is something real, and they are referred to as skeptics. Now, the skeptics argue that unlike what the globalists would have us believe, that there are things and ideas and people that are traveling across the world, across multiple borders, and that we live in an interconnected world, actually there are many parts of the world and many types of people who are completely left out of these kind of global flows. So, they would give you the example of typically indigenous communities who live across the world. And they would argue that if you look at the lives of indigenous communities, particularly tribes that are quite isolated in terms of their physical location, their lives continue without their participating in any kind of global flows. To this, the globalists would respond that even though people may live in isolated and remote locations, and they may not be directly involved in global flows, their lives today are still being influenced by events that are happening at a global scale. You can take the example of climate change. So, for instance, if there is an indigenous community that has no contact with anyone else in the world apart from themselves, but they live in an area which is experiencing an increase in sea levels, an increase in the temperature. All of this may be attributed to people in neighboring countries, or actually rather events that are happening across the globe. So, in that sense, even though you may not be directly participating in global flows, your everyday life is affected by what is happening around the world. Another argument that the skeptics make is in regard to what happens with the nation states. Now, initially when discussions about globalization started, and we are talking about the 1990s, the expectation was that the nation state as an entity is going to wither away. It's going to cease to be important. Now, skeptics could point out to the world today and say, well, nation states are still important. We still live our lives based on which nation we were born in or which nation we have citizenship in. Their rules and regulations are still important for us. To which globalists would argue that this expectation that the nation state will cease to be important, that itself is a fallacy. Rather than facing a situation that the nation state becomes less important over time, we actually may be headed towards a situation where in addition to the nation state, there are other laws which become important to our lives, and they shape our lives on an everyday basis.